next-gen health monitoring. So hope my screen is visible to all.
Yes, sir, it's pretty
Yes,
much
sir.
visible.
Yeah. Okay. Thank you. Let us see the outline of this webinar. So I will start with the uh, uh, classification of different biomedical antennas, such as ingestible, implantable, and injectable. Then I will try to explain briefly this biotelemetry system and the EM spectrum, specifically related to this biomedical antennas. Then we will also discuss some challenges and the flow chart, which could be useful for the designing and fabrication of this biomedical antennas. Then I will show you some research work which have been done by us in last couple of years, and which are specifically related to this MIMO antenna systems for wireless capsule endoscopy and transcatheter pacing system, which can be used for your heart monitoring or to control the pace of heart. Yeah. So as we know that antennas play a crucial role in wireless applications, and it's a antenna. If we say, whenever we listen to this word antenna, the thing comes to our mind is Yagiuda, right? Which we usually see on the terraces. These days they have become obsolete, but previously they were used in all houses for the broadcasting or like receiving signals from the TV stations. But with time, the antennas have been transformed, and now they have become part of all wireless systems, either it is smartwatch, cell phones, or smart gadgets, or any other XYZ device which has some wireless functioning. So basically, these biomedical antennas, they are quite different from the traditional, or we can say conventional antennas, because they're smaller in size, they have a low profile, and the main challenge is to implant them over the body or inside the body. So we will go through all these challenges in this webinar, and I will try to take some questions also related to these kind of antennas. So here we can see in figure 1, uh, different types of wearable antennas are shown, and they can be used for this insulin sensing, electrocardiogram sensing, temperature sensing, motion sensing, or blood pressure. And these kind of systems can be collaborated or connected through an IoT gateway, and the data can be shared through cloud to monitor the human health. Here, this picture shows an implantable system where different medical devices have been shown, and they can be used for different applications, such as uh, cochlear implants. They can be used to improve the hearing. Pacemakers, it's almost like, I mean, this is known to most of you. We can use insulin pumps also. They can be implanted inside the body. Foot drop. Another thing is gastric stimulators, which can sense the stomach health, and deep brain neurostimulators. I think this kind of thing is like quite popular these days due to Elon Musk. They are doing some experiments on these deep brain stimulators. So in short, We can say that biomedical antennas, they can be classified as off body, such as wearable antennas, on body. They can be either on, or they can be a combination of on and off, and in body, which are implantable devices or implantable antennas. So why these days these biomedical antennas are quite popular? Since we know that India is a I mean this I mean we have a huge population, and most of us have one or the other issue due to aging or due to our like day to day lifestyle. So we have an estimated 1.5 million patients affected by this inflammatory bowel disease, and we are just second to the USA, because they have more than 1.6 million patients suffering from IBD. And this, the public health estimates indicates that India accounts for approximately 60% of the world's heart disease burden. So we have like maximum people suffering from heart disease, or we can say almost 60% of the population data related to heart disease. And so these rapid advancement in biomedical devices can offer some solution to such problems, and they can be a transformative opportunity to address these. Here I have shown some biomedical implants, and such as these implants can be useful for epilepsy stimulator. They can control vagal nerve, cardiac, and spinal cord implant. So these are some plants which are used across the world, or they are in testing stage. If they are not available in the form of a product, they are in the testing phase. Now let us see the classification of different in-body antennas. So as I have told that we are going to cover three types of in-body antennas: ingestible, plantable, and injectable. So these ingestible kind of antennas, they can be used to diagnose or to monitor gastrointestinal infections, okay, in which a person will swallow the antenna, and the antenna will travel to the small intestine of the patient, and we can monitor the condition of the small intestine by the help of this gastrointestinal antenna. The next type is implantable, and one of the most popular example for implantable is a cardiac implantable antenna, which can be placed inside the pacemaker. Then we have neural implants and retinal implants. Then injectable, which is quite a new term, and it is like people have just started working on these kind of things, injectable antennas, and they can be used as a microstimulator. They can also be used for glucose sensing and oxygen sensing. So we have done some work in these three types of in-body antennas, and I will present my work also in the later slides. Uh, these are some features of these three antenna types, like about their placement and the purpose. So here we can see these injectable antennas, they are directly placed into body tissues, and they allows wireless data transmission for health monitoring or short-term diagnostic applications. The other two types, they will go inside the body or within the body, usually under the skin, muscles, or within body cavities. And they can be used for data sharing through an external system. Now let us see the first type, injectable biomedical device. And for this kind of system, uh, we coined this term as capsule endoscopy or wireless capsule endoscopy. If you go through the papers, you will see it is written as WCE, wireless capsule endoscopy. So as we can see in this figure, uh, this the patient is swallowing a capsule which will go through this food pipe into the stomach of this patient, and then it will travel through this small intestine. And here this is the enlarged view of this small intestine. As you can see, this capsule is traveling inside this intestine, and the camera view of this antenna or capsule will be like this. You can directly see the view on your screen. So this is an example of a commercial capsule which is available in the market, used for wireless capsule endoscopy. And this capsule is PillCam Crohn's capsule. And the length of this capsule is 32.3 millimeter. And the dia of this capsule is 11.6 millimeter. You can see here. This is another type, Microcam 2000 double tip capsule. And here a camera is placed on the front end of this capsule to diagnose the health status of this small intestine. So these are the procedure or the steps which are followed for the wireless capsule endoscopy. So this capsule glides smoothly through the digestive tract, and the camera inside the capsule will capture images and transmit data to the external antenna system. So here the advantage is a doctor can examine the condition of this small intestine in real time, and this capsule can naturally excreted. Okay, and these are the advantages of this process. It is a non-invasive process, it is painless, there is no need to give sedations to the patient, and it offers 3D color images as compared to x-rays or other uh, diagnostic methods. It offers 3D color images without any surgery. But there are few limitations also. The first limitation is incomplete small bowel examination. The second limitation is this capsule has a limited battery life and no therapeutic or biopsy capability. So I hope the problem is clear to all, or the application, what is the purpose of using this wireless capsule endoscopy, and what is the role of antenna inside this wireless capsule endoscopy system. The next thing is leadless pacemaker. So this is a commercial leadless pacemaker. First of all, I'll tell you what is the purpose of using this pacemaker. A leadless cardiac pacemaker, which is popularly known as LCP. So it is used to control the heart rate of the patient. It is placed inside the heart and prevent slow heart rates. So here this process has some advantages. There are no need of wires. Because of this reason only, it is known as lead less without any wires. And there are few limitations also. It can only pace one ventricle, it can't defibrillate, and it has a higher cost. So this is the process to place this leadless pacemaker inside the human body, and you can go through the steps. I'll just show you this thing. This is a commercial leadless cardiac pacemaker available in the market, and the name of this LCP is nanostim LCP. This is the size of this pacemaker, and you, as you can see here, this is placed inside the heart. This is another kind of pacemaker which is known as micro TCP. Okay, so basically what we have done on the transmission part of these pacemaker and endoscopy system. The next type is injectable, and this injectable biomedical device can be injected inside the body for the monitoring purpose, and it is a minimal invasive process because this kind of uh, device is injected by the help of a syringe, like a injection. And these devices use wireless technology for data communication and energy harvesting. The advantage is it is minimally invasive, the placement is flexible, and there is no need to give sedation to the patient. Again, the disadvantage: limited power capacity, limited functionality, and the cost is high. So here we can see few examples of injectable biosensors. So this is one of the biosensor known as phosphorescence biosensor. Another type is implantable RFID computer chip, which is about the size of a rice. And it was commercialized by Applied Digital Solution. You can see the picture of this uh, RFID computer chip. And another thing is Medtronic insertable cardiac monitor. This is the uh, system, implantable system, and it was designed by this Medtronics. This is name of a company. Now, how the biotelemetry system works for the monitoring, telemetry, stimulation, and the treatment of a patient. So you can see this is a human body, and we have also shown different types of implants that can be placed inside the human body. And so these implants will report to the base station. The information from these different implants will go to this base station, which is connected through your cell phone, or it can be connected through some uh, cellular device or wireless device. Then this medical information will be shared through a wireless network to the cloud server, then to the hospital. And according to the information shared by these implants, a doctor sitting in the hospital will take the necessary call. In case of an emergency or SOS call, the ambulance will be ready and it will be carrying the patient to the hospital. Right now, this telemedicine is quite popular. I mean, after post COVID, these things are popular inside our country also. So, but telemedicine is just a small part of the biotelemetry system. because this telemedicine is just an application of this biotelemetry system. In biotelemetry system, the complete care of the patient is taken care by this technology, and the data will be auto shared to the hospital or to the doctor. This is the EM spectrum for biotelemetry services. Here I've tried to cover United States, Europe, and Indian bands. So these are three bands which are oftenly used for biotelemetry services. The first type is medical implant communication service band, or popularly known as MICS. So here we can see the frequencies are same across the world. A band of 402 to 405 megahertz is used in all three places. The next band is wireless medical telemetry service band. In US, it is classified into three bands: band 1, band 2, and band 3. In Europe, it is classified as band 1 and band 2, whereas in India, we use a frequency range of 608 to 614 megahertz in this WMTS. This is Industrial Scientific and Medical Band, ISM band, and it is further classified as band 1, band 2, band 3, and band 4. Basically, band 1 is used for low power devices, band 2 is used for short range communication, band 3, popularly used band, which is used for Wi-Fi and Bluetooth, and band 4 is also used for Wi-Fi and high data rate communication. Now, let us see the design challenges in biomedical antennas. The main design challenge is the attenuation of EM signal, because here we are playing with the human body or human tissues, and human tissues, they absorb RF signals, due to which signal attenuation, scattering, and feeding will occur. So which leads to reduced signal strength, or it will completely change the performance of the antenna. The next challenge is limited radiation efficiency and impedance matching problem. Because of small size of the biomedical antenna, the gain is less, efficiency is less, and again impedance matching could be a problem. Also, these antennas must be designed on biocompatible materials to ensure compatibility with the body and minimize any adverse reaction. Next problem is to eliminate the batteries or wired connection in the biomedical devices. So for such issues, few people have proposed this wireless part transfer technology, which can lead to self-sustainable biomedical devices. Again, the selection of operating frequencies, as I have shown in the previous slide, we have to choose frequencies very, very carefully. And to choose the implant position and orientation is also a challenge in such antennas. Also, we have to adhere to strict regulatory standards and guidelines. So there are several guidelines which are given by National Institute of Health and Federal Communications Commission and other regulatory bodies with respect to specific absorption rate, with respect to uh, uh, size, packaging, material. So we have to follow those guidelines before going for design. Now these are specific to ingestible, implantable, and injectable antennas. So in ingestible antennas, the main challenge is the frequency detuning, because the capsule will travel inside the food pipe, it will travel inside the stomach, colon, and small intestine. So uh, the antenna performance will get changed because of different nature of the body parts. In most of the devices, we use single input, single output antennas, and the main problem with SISO antenna is it has a reduced data rate, poor reliability in multipath environments, and performance degradation caused by body tissues. And another thing is a miniaturized capsule is required. Okay, so again, if you reduce the size of the antenna, the performance will degrade. And the third type, injectable, it must be a compact size antenna, and it could be a size of this 3 to 4 millimeter, so that it can be implanted inside the tissues. Now these three types are further classified as SISO, single input single output, and MIMO, multiple input multiple output antennas. This is the design flow chart of a complete biomedical process. In the beginning, we choose application. Accordingly, we choose the operating frequency. Then the capsule size and material is chosen. Then the type of antenna is selected. Then accordingly, we calculate the length of the antenna or the size of the antenna. Then antenna is simulated using simulation software. Then the antenna is simulated inside human tissue phantom in the simulator only. Then accordingly, we optimize the length, width, gap of the antenna. Then let's say if the antenna meets the specific requirements, then you can go for the next stage. Otherwise, we have to again optimize the antenna size, antenna design, and then again follow the same process. Let's say if the requirements are met, then we simulate the antenna inside the heterogeneous human model. Then simulations are again run in heterogeneous human model. If, let's say, again it meets the requirement for plantable system, then RF safety analysis is performed. If things are going in the right direction, then we can go for the next step, which is validation step. Otherwise, we have to again do this reverse engineering. In the third step, we go for fabrication, testing, and then clinical trials. So if, let's say, uh, testing in the testing part, we go for in vitro and ex vivo, both types of testing, in which the antenna is tested inside the pork meat or phantom solution. Then further, we compile all the results and do clinical trials. Now let us see the first type of this antenna, which can be used for wireless capsule endoscopy, and we named this work as conformal wideband MIMO loop antenna system supporting multi-channel communication. This is the history of wireless capsule endoscopy. It dates back to 1980 when a team of engineers and physicians in Israel, they developed a prototype, and this company was the first one to launch this prototype. And in 2000, this company, Given Imaging, they introduced a M2A capsule. This is the M2A capsule picture. Okay, M2A means mouth to anus, and it was the first commercially available wireless capsule endoscopy system. Then after 7 years, they launched another version of this M2A, which was an advanced version of this, and it was named as PillCam SP2 capsule, which has a higher frame rate and better image resolution. Further, some specialized capsules have also been developed for imaging the esophagus and colon. WCE systems available in the market, endocapsule, PillCam. Okay, so these all are this is a cross-sectional view of the wireless capsule endoscopy cap system. Here we can see the first thing is outer shell, and usually the capsule shell is made up of biocompatible alumina. Again, these are the dimensions of the capsule shell. And superstrate superstrate is placed here, which is made up of polyamide material. This figure is taken from one of our published paper only. Okay, so he is my PhD student, L. Harlan. So we have drawn this figure by ourselves. If you want to see more details of this, you can go through this paper, which was published in one of the conference. Then antenna module, which is third part. This is the antenna module part. Okay, here you can see the detailed view of this antenna module. Then camera, PCB substrate, circuitry, battery, LED, etc. Okay, and these are the
Sir,
specifications.
sir, there is
Yes, sir.
one query probably from K. Ibrahim J. So, would you like to take that now?
Yeah, yeah, fine.
Please, Ibrahim, please go ahead with your query.
Can you can you uh, tell me the question, because I cannot see the chat.
Question is not into the chat. He just raised the hand.
Okay, okay, then he
Oh,
can ask.
hello, Ibrahim, are you there? Okay, sir, please go ahead. Continue.
Hello? Hello?
Hello.
Yeah, are you speaking with me?
Yes, yes. You raised your hand. Probably you
Yeah,
have
yeah,
some.
yeah, yeah. I did. I don't know. Is a very nice presentation. Thank you so much, Doctor. I just want to draw us back to the materials that you said was used. The question goes like this: Okay, now for how long can it stay? I mean, the material that will be injected to the human body, for how long can it stay in that body? Can it sustain itself inside the body of a human tissue? That is my question. Thank you very much.
Okay, okay, yeah,
Yeah,
okay, sir.
thank you.
Yeah,
Thank
actually,
you.
this capsule will stay inside the body just for few minutes, because I think few minutes are sufficient to take the uh, images of our colon or small intestine. So it will stay for few minutes, and within these few minutes the doctor will diagnose the internal organs of the body, and then it can be secreted by the anus part. Hope my answer is clear to you.
Yeah, very clear, very straightforward. Thank you very much, doctor. Thank you.
Thank you.
Thank you. Yeah.
So let us move to the next slide. This is the simulation setup which we have created in the software CST Microwave Studio. And here you can see this is the radiation box of this uh, system. And what we have done, we have taken the permittivity of different body organs such as intestine, muscle, colon, and stomach. Okay, and these are the permittivity value. Those who are working in this domain, they can note down the values also, and they can use further for their research. So here what we have done, we have created a setup in the form of a cube, and the size of this cube was 100 millimeter into 100 millimeter. And the capsule which we have created inside the software along with antenna and other periphery, we kept inside this box or cube. Okay, and we have then done our simulations. So you can see the okay, I will show the simulation part in the next slides. So here you can see the antenna design. So this is the antenna design, and it starts as a simple rectangular loop, and it offers a wideband characteristic. So this equation is used to calculate the resonant frequency of this antenna. Then what we have done, this is an illustration of single input, single output antenna. So what we have done, we have used two antenna elements. So this is a detailed view of this single input, single output antenna. You can see the dimensions also. These all dimensions are available in the paper also. If you want to see a detailed view, you can go through the paper. Here, since the time is less, so I will just go through the like overview part. This is the top view of this antenna, and this is the bottom view. So here thicknesses are also given, and this this is this antenna is created on the polyamide substrate, and the copper thickness used was 35 micrometer. Then alumina thickness and camera PCB, everything is considered during the simulations. And this is the reflection coefficient of this antenna in different body parts. When we kept it in muscles, when we kept it in stomach, when we kept it in small intestine, and when it was kept inside the colon. So you can see the behavior of this antenna is more or less same in different environments, and it is basically covering all biomedical bands: MICS, WMTS, and ISM frequency. So it is covering almost all the three frequency bands which are used for biomedical applications. Then you can see the radiation patterns at different frequencies, specifically related to these three frequency bands. And it the antenna offers a bidirectional radiation pattern. at 0.402 gigahertz, 0.433 gigahertz, and 1.4 gigahertz. And it offers like an omnidirectional pattern at 0.915 gigahertz and 2.4 gigahertz. Then MIMO characteristics are calculated for the same design by using two elements. So these are some general equations which you can easily find in any of the book on MIMO systems. So, and these 5-6 parameters are usually considered while designing any MIMO system. So here we have considered envelope correlation coefficient, which is calculated using this formula. Diversity gain, using this formula we can easily calculate diversity gain, mean effective gain, channel capacity loss, and total active reflection coefficient. And their ideal values are also given, because many of you are not working in the communication domain. So we have given some ideal values and the practical values also, which are acceptable by standard organizations. So now let us come to the modified version of this wireless capsule endoscopy system. So previously we have designed a single input, single output system. Now what we have done, we have modified our previous system and we have changed it to a two element wireless capsule endoscopy system, where two antenna elements are used for sensing the internal organs of the body. Again, the dimensions are as follows, and materials used to simulate these different parts are mentioned here. And if you want to see a detailed explanation of this thing, you can go through this paper, which was published in 2024, last year. Now, what we have done for this MIMO system, we have designed a heterogeneous model in which we considered skin layer, a fat layer, and a layer with intestine, muscle, colon, and stomach. So these are collectively written as layer 1. And again, the antenna was implanted inside this setup, which was created in CST Microwave Studio. And the antenna performance was studied. So you can see the evolution part, which is quite similar to the SISO antenna. But here, instead of using one element, we have used two elements for the antenna system. So I'll not go into the sign part again. This is the S11 performance of this antenna, and you can see the final design. The curve is shown in this light green color. So this is the performance of the proposed antenna system. And again, it is working at MICS, WMTS, and ISM frequency bands. So basically, it is covering all the frequency bands which have been assigned for biomedical applications. This is exploded view of the MIMO antenna system. So again, the dimensions are given here. This is the top view and the bottom view. So it is quite similar to the SISO one. The only thing is, instead of taking one element, here we have taken two elements so that it can completely cover the capsule part. Because in the SISO antenna system, it will only partially cover the body organ. So here you can see it is 360-degree covering the capsule part. These are the simulated S parameters in uh, different models, homogeneous as well as heterogeneous. So here we can see S11 and S22. Basically, S22 represents the isolation, sorry, S21 and S12 represents the isolation between antenna element 1 and antenna element 2. And S11 and S22 represents the reflection coefficients of this antenna, post 1. So you can see that it is covering the entire frequency range, basically a band of 0.1, 0.3 to, and it is going up to 2.6 gigahertz. So it is covering a large frequency band. And the antenna performance was checked inside the colon, stomach, small intestine, and muscles. This is the experimental setup which we created in our lab. So this is the fabricated antenna. You can see the antenna was wrapped on the capsule. Okay, we can see two elements as element. This is antenna element 1, this is antenna element 2, and both these elements were wrapped on the capsule, and the testing was performed inside the phantom solution and the poke meat in free space as well as inside the anechoic chamber. And the phantom was created using these salts and water, and it is just similar to the human, the permittivity of the human body organs. You can see the results of the simulated and measured system, and we can see the bandwidth here. It is going around it is around 2.2 gigahertz. This antenna offers a bandwidth of 2.2 gigahertz, and uh, this represents the isolation between antenna element 1 and antenna element 2. And we can see that the isolation is greater than 20 dB between these two antenna elements. These are the radiation patterns in the E plane and H plane at different frequencies in the 3 bands. So you can see the patterns are almost bidirectional in the E plane and almost omnidirectional in the H plane. Then we check the MIMO performance of our antenna design, specifically envelope correlation coefficient, diversity gain. So we can see the results of ECC and diversity gain here. So this ECC was less than 0.5, which is a standard value of ECC, and diversity gain, it should be around 10 dB ideally. So here we can see it was close to 9.6 dB. Then mean effective gain was calculated, and the antenna has a power ratio of less than 3 dB as per the requirement that it should be plus minus 3 dB. So here we can see it is somewhere lying around 0 dB. So it is also following the standard process. Then channel capacity loss was calculated, and it was less than 0.4 bits per second per hertz for all the 3 bands. Then torque was calculated, which should be around less than minus 10 dB. So this torque was calculated at different phi at 0 degree, 90 and 180 degree. Of course in simulation, but in measure due to some limited resources, we checked it at bore site axis only, which is phi equals to 0 degree. And then link margin was calculated. So this antenna, the MIMO antenna, can create a stable link across distances up to 6 meter, 7.5, and even greater than 20 meter at data throughput of 120 Mbps, 78 Mbps, and 1 Mbps. So the transmission, reception, and signal quality values were calculated, and they are presented here in this table. Then SAR, which is an important parameter in the case of biomedical antennas, which is an acronym of specific absorption rate, that how much power will be absorbed by the human body. So there are some standard guidelines which are 1.6. This power must be 1.6 watt per kg for 1 gram tissues and 2 watt per kg for 10 gram tissues. So what we have done, we have considered a human voxel model in the CST software to examine this specific absorption rate. And for this examination, we have placed this antenna capsule system inside the small intestine, colon, and skin fat. You can see it was placed inside this human body at position 1, position 2, and position 3. So here you can see the SAR values at different frequencies and different positions. At position 1, it was placed inside the small intestine. Position 2, it was placed inside the colon. And position 3, it was placed inside the large intestine. And the values are calculated at 1 gram of tissues as well as 10 gram of tissues. And the maximum allowed power was also calculated. So I think this is clear to all. If you have any questions, we can discuss them now, and then we will move to the second research paper. Yes,
Our
please.
participant, Mr. Mahfouz, can you please ask your inquiry?
Thank you. It's a nice presentation from Bert. Could you please go slide number 36?
Okay. Yeah.
I can assume.
Yeah. This one.
It's supposed to be 26. Yeah, 26. I just missed it. Sorry.
Slide 36 probably he asked for.
Yeah, 26.
This is slide number 36.
Talking
Can you tell
about
me the
slide number 26. 26.
26. Okay. Yeah, got it.
Yeah, correct.
This one.
Yeah. So I have one question. You implant the antenna inside the body. So how much the input power do you consider for the simulation? I'm talking about
During
the
this
input power.
given to the antenna system.
Exactly. When you place the antenna inside the human body, okay, and how much input power you assign for the CST for the simulation?
Okay. Yeah, actually input power will be when we do simulations in CST, it will provide input power according to the frequency. Since here the frequency band.
Your next stop is 2 minutes. Also, we are on time right now. Avec Alexandria, donc je vais dans 2 minutes. Pas plus avant à l'heure.
Okay. Yeah. Here the frequency band was considered a lower frequency band only, which means this we have targeted MICS, WMTS, and ISM. So hardly it is going up to 3 gigahertz. So the input power would be very small because it will be in milliwatts if you calculate the overall power, because this capsule will be powered by the help of a small battery. When it goes inside the body, inside the human body, it will be powered by the help of a battery. Okay, so very minute power is required to share information from
I know
inside
this
body.
antenna will become what I know this antenna becomes a picowatt level power. But my question is
Yes.
that when you assign the antenna from inside the body, how much input power you assign in the CST software to the simulation in CST, HFSS, or FEG or radius? How much power you will assign for the simulation? This is my question. So from this body environment will get the SR value for 1 gram and 10 gram uh, tissue, right? So my
Okay,
question is
understood.
that how much input power will give the input in the simulation tools for this simulation, maybe 0.5 watt or less than that. I don't know. Just I'm asking you that how much power you did for that because it's the implantable biomedical antennas, right?
Right. Actually, in CST, we do not give any input power. We just assign the frequency, and based on the frequency, it will excite the antenna. When we do simulations, there is no need to assign any input power. We just check the S11 pattern on based on the input frequency.
All right. Thank you very much, Dr. Shoti. Gupta, maybe
Yeah,
if I have
thank.
any more question, I'll give an email.
I'll be happy to answer your question. Thank
Bye
you.
Sure.
bye.
Thank you, Dr.
Thank
Mathi.
you.
Bye.
Any other question?
There have been a discussion on going on to the chat in this webinar. Uh,
Hmm.
they are concerned about the biodegradable battery. If like the battery stuck into this body inside, then
Okay.
is there any side effect of that?
No, actually, the antenna capsule is a biocompatible material, and the battery will be placed inside the capsule. Obviously, there will be side effects if the battery becomes out of the capsule, but the capsule is designed in such a way that the battery will not come out of the capsule when it goes inside the body.
So basically, it's not biodegradable as if now, and the whole
No,
capsule will come out of the body.
right. Only the
Okay.
capsule is made up of biocompatible material, because
Okay.
there, as of now, there is no such battery which is biocompatible or which is compatible with the human body. But if we take an example of pacemaker also, pacemaker also use a battery in order to power up itself.
Very true.
Okay, so
Okay.
I
Thank you,
think
sir.
my answer is okay. So shall we go further?
Sure. Sure. Please.
Okay,
Sir,
so
I
this
have a
is,
question, sir.
yes sir.
Excuse me. Sir, how to decide the input power in CST software according to frequency? The
Sir, there is no need to choose any input power in CST software. It will take, it will ask only frequency, only the assigned frequency band or the operating frequency band. It will automatically convert this input power, and it will run the simulations. So when we go for simulations, when we do simulations, there is no need to choose any input power. You have to choose only the frequency range and the band of operation.
okay, sir. Okay, thank you, sir.
Hello, sir.
Yes.
Actually, for SAR analysis, I think input power is given, is needed for SAR analysis.
Okay.
So, how much input power is given in this antenna?
Yeah, in for SAR analysis, I have already mentioned the transmit power is 1 watt. Okay.
Okay. Thank you, sir.
Yeah.
Excuse me, sir. I have a question, sir.
Yes, sir.
Sir, what might be the lifetime of the battery, sir?
Sir, actually, it depends on the quality. Few batteries will run maybe for a year, like, and few may run for more than a year also. It depends on the quality, on the brand. Similarly to our cell phone batteries, because mostly lithium ion batteries have been used. So, but the problem is, like, after few times you cannot use the capsule again and again. So obviously, it can be used for limited number of times only.
Okay, sir. Okay. Thank you, sir.
Okay, sir. Thank you.
Moreover, sir, I think regarding the power, because I have also worked once for the antenna, and that was for it was capturing the power into frequency into megahertz. So in that case, we were able to generate the power which can light a LED bulb, LED, the small LED of few watts. So probably when capsule is inside the body, then there would be very less power, because if it would be higher into the body, it will give the shock to heart also. So it might be into picofarad, and it
Yeah,
obviously calculated by the frequency which we are using. Small frequency gives small power.
right. Just just to transmit the signal, power is required from body to the outside antenna or the outside base station.
Yes,
So
and it's not having high range of for transmission. It's just
yeah,
nearby within 1 meter.
within 1 meter, 2 meter, hardly 2 meter. So it's a short distance communication system only. So we need very small power in microwatt or picowatt. It's fine. So shall we start this?
From Samira.
بیا دیگه
Sir, can we take one more question from Samira?
Yeah, yeah, we can, we can.
Hello, sir.
Yes, ma'am. Yeah, hello.
Hello, sir. How can we access the full webinar recorded video?
I think Dr. Abhishek will help you in this case, because I think he has only the admin rights. So he may help you.
Can you please come again? I probably lost the question.
I think she wants to watch this webinar as a recorded video.
Yes,
So
yes.
maybe you can share the recorded link with her so that she can watch it later.
Sir, I have one more question.
Yes, sir.
Take the first.
Sir,
Thank you, sir.
how to calculate the, sir, maximum allowable input power for the antenna for SAR calculation?
Okay. Sir, actually, as of now, there is no process to measure it in India,
Okay.
because in cell phones also, these things are measured either in Korea or Taiwan or China. We do not have measurement set up in India. Because of this reason, we are not manufacturing any such things in India. Or if we want to measure also, we have to go to some country. I mean, these countries which have such facilities, and then you can measure them.
Okay.
Here, I'm just talking only about the simulation specific absorption rate, or the calculated one.
Okay, sir. Thank you, sir.
Yeah. Yes, sir. So, Dr. Abhishek, how much time do we have? Uh, uh, Dr. Abhishek, am I audible? So Am I audible? Abhishek,
Yes, sir. Yes, sir.
how much
Trailer start.
time do we have now? Because it's already 7:40.
No problem, sir. We can wind up now, and if there would be any other chance to connect again, then we all will be connecting, right?
Okay, so I will just share some slides related to this summary, and maybe in another session we will take on this transcatheter pacing system or implant or this injectable thing, right? Because I have few more things to share, but since the time is less, so what I will do, I will just discuss a few more things. Here you can see this is the performance summary of SISO and MIMO system. So here you can see the uh, difference between their performance. Actually, the conventional systems or the technology available as of now, they use SISO system for implantable devices. So what we are trying to replace these SISO systems with MIMO systems. And we are not changing the size of the device. We are not changing the size of the PCB, which is placed inside this capsule or transcatheter pacing system. We just only change the antenna type so that a complete diagnosis can be done without changing the equipment or without changing the existing infrastructure. So here you can see the simulation setup and operating frequency range, which we have covered for SISO as well as MIMO system. And these antennas are used on the inner wall of the capsules so that space can be saved. Also, we have considered a simulation box of this much size, and the antenna was penetrated inside this simulation box, which is a homogeneous model and heterogeneous model. So you can see, if you go through the research related to these biomedical, you can easily understand what is homogeneous, heterogeneous, and how the performance is changing from a homogeneous model to a heterogeneous model. And so here you can see we have used two elements, and the isolation between these two elements was achieved greater than 25 dB. Okay, and maybe in some other session we will discuss this injectable thing also, because today, since it is already more than 1 hour, and it will take another hour if I start this injectable. So here you can see this injectable was also designed on flexible substrate along with two elements. So this is the geometry of this injectable antenna, and this injectable antenna was working at 3 frequency bands. Previously, the antenna which we have designed for wireless capsule endoscopy, it was working for a wide band, whereas this antenna is working at 3 specific frequency bands. You can see here, and these are the 3 frequency bands, and we tried to cover this ISM frequency bands. Okay, so here you can see the bandwidth, and the elements were 2, and the isolation between these two elements was greater than 17 dB, which is a good value. And again, this study was performed inside a homogeneous model, a a 3-layered phantom model, and a heterogeneous hand model. And the reconfigurability in where in reconfigurability means what we are doing, we are changing the frequency band of this antenna by using a diode. So I will just come to the conclusion part. So here a conformal multi-channel single input single output and multiple input multiple output loop antennas were demonstrated for injectable and implantable applications, and these 3 frequency bands were covered, and the miniaturization was achieved using meandered loop structures. In order to keep the antenna compact, what we have done, we have used loop structures or the meandering geometry. And the detuning effects of the antennas were studied in homogeneous and heterogeneous model. Later, the antenna was also fabricated and it was measured inside the poke meat and phantom solutions. Then MIMO performance was demonstrated in terms of ECC, diversity gain, and SAR analysis was also performed. And these can be some research objectives which those who are working in this domain, they can choose for their future research. They can further work on the miniaturization and better integration of antennas with biomedical devices. They can encounter the effects of tuning, again biocompatibility, which is a challenge in such antennas and biomedical devices. In vivo testing, for clinical trials, we need permissions from the government as well as hospital has to allow, and advanced simulation models, because as of now the models available in the CST or HFSS, they are simple human models, but for such analysis we need complex human models where we can easily place the antenna considering all the factors of human body, because in this study we didn't consider human blood, human sweat, but these factors also should be taken into consideration if we are going for a thorough analysis of a biomedical device. So these are
Thank you,
some
sir.
references which could be useful for your study. So thank you.
Thank you, sir. Thanks for your insightful session. And I can see it is very quite engaging also. Our participants have shown very much enthusiasm and they came up with a lot of queries. And still there are many queries left into the chat box I can see, and I'll be sharing those queries with you personally, and will
Okay.
request you to please answer so that I can share with those all. And
Okay.
from our other participant behalf, I would thank you a lot, Dr. Sachin, for your time and valuable session. And I can see into the chat also people are asking for workshop too. And fortunately, we have planned the workshop also into the coming time. And but because Dr. Sachin is very tight under time, and we need to buy a coffee for him for motivation, so I would request our participant to support the time of Dr. Sachin, so that there would be more motivation to join the workshop. And fortunately, because we are running and his time is very valuable, so we are offering a very huge discount on the workshop session. It's very minimal, like a coffee. So I would request all the participants, those who are interested into the upcoming workshop, to pay a little amount for the workshop. Links are shared onto the chat and this WhatsApp too, and onto your mail also. So if you will join and interested in the workshop, I would request to confirm your seat by today itself at the discounted price. and motivate Dr. Sachin and to value his time also. And Dr. Sachin, I can see there is a very good feedback from the participant also. So I think that's very motivating for us also. And it's very, of course, I am no one to justify or say anything and anything on your credibility. You are very much popular already. So thanks for your time, and thanks once again to everyone for this time and for this session. And we'll be happy to take your queries onto mail also, so that I'll forward that to Dr. Sachin, and will answer your queries. You can reply directly onto the email which you have received so far. And I am so sorry once again to fill up your mailbox by our mails. I just wanted to make sure that maximum to maximum people reach to the webinar and get the insights of this high-tech antenna. So thank you and once again.
Yeah, thank you.
And
Thank you for having me here. It's a pleasure to interact with such enthusiastic participants. And we'll take all your questions and we will get back to you with relevant answers. Thank you very
definitely.
much.
Thank you, everyone. Have a good night. Have a nice day. Bye bye.